Hi, everybody, and welcome to 10-2 Regression. Key concepts. This section presents methods for finding the equation of the straight line that best fits the points in a scatter plot of paired sample data. In the last section, 10-1, we looked at the correlation. We saw that there was a line that would best fit the points that were given. Now we're going to learn how to find the equation of that line. The best fitting straight line is called the regression line, and its equation is called the regression equation. Then we discuss marginal change, influential points, and residual plots as tools for analyzing correlation and regression results. The regression line. Given a collection of paired sample data, the regression line, or the line of best fit, or it's also called the least squares line, is the straight line that best fits the scatter plot of the data. I have a graph and I have some points. There's going to be some line we'll call the regression line. It's also called the line of best fit. It means the line that works best with the data points that were given. If I were to measure the distance from that point to the line, then square it, then pick another point, and so on. There's a distance. If I squared the distance, I would have 1 squared plus -2 squared plus, and so on. If we add all those values up, we get some number. That regression line, or the line of best fit, is when this number is the smallest it can be, which also would be the line where all the points are the closest to it. The regression equation, y hat is equal to b0 plus b1x. The regression equation expresses a relationship between x, which is called the explanatory variable or predictor variable or independent variable, and y hat, called the response variable or dependent variable. We can always express a line in terms of this equation, where m is equal to the slope and b is equal to the y-intercept. This is in different form. If I took this equation and I changed it to y equals b plus mx, and then this b is called b naught, then that's still the y-intercept, and the m is equal to b1, it's still the slope. The equation that you see is still the same as y equals mx plus b, it's spun around. In this example, y equals mx plus b, x is called the independent variable and y is called the dependent variable. Because when we have an equation, we pick an x and then we solve and we get a y. Y equals mx plus b. Let's say we have y equals 2x plus 3, and I want to graph it. There's a couple of things I can do. This is my y-intercept, 1, 2, 3. This is the slope, and the slope m is equal to the rise over the run, which is equal to the change in y's over the change in x's. If my slope is 2, that means for every 2 I go up, I go over 1. If I want to make a line, I can connect those two dots. If I have y hat is equal to b0 plus b1x, that's the same as saying I would have 3 plus 2x. This has a positive slope because if I read from left to right, it's going up. As x increases, y also increases. If I have a negative slope, notice how as x increases, y gets smaller. This has a negative slope. This has a positive slope. Why do we call x the independent variable? and y, the dependent variable. If I want to solve this equation, I can pick any x value that's independent. If x equals 0, when I plug it into this equation, 2 times 0 is 0 plus 3 is 3. My y equals 3, and it depends on what x was. If x is 1, 2 times 1 is 2 plus 3 is 5. If I pick 2, I have 2 times 2 is 4 plus 3 is 7. The distance between each one of these is 2, which is my slope because I'm going up 2 and over 1, which is my rise over my run. X is called the explanatory variable or predictor variable or independent variable. I showed you why it's the independent variable. It's also the predictor variable because when I pick a value, it's going to predict my value of y. And then y hat is called the response variable. We predict something and then we have a response. Finding the equation of the regression line. Notation for the equation of a regression line. For the sample statistic, it's B0, B1, y hat equals B0 plus B sub 1 x. For the population, it's beta sub 0, beta sub 1, and our actual y. Y hat is an approximation of our y. What are the requirements of the regression line? First, the sample of paired data is a random sample. It has to be quantitative data, which means values. We have to have a way to graph them. Visual examination of the scatter plot shows that the points approximate a straight line. If you look at it, you can see a pattern. The pattern is as x gets bigger, y gets bigger. That means it's going up. This is x and this is y. Also, we can have a line that goes down. As x gets bigger, y is getting smaller. This would be a positive slope. This would be a negative slope. And it has to approximate a straight line. It doesn't have to be a straight line. Number 3, outliers have a strong effect on the regression equation. Remove any outliers if they are known to be errors. You don't want to just remove points unless you know you made a mistake somewhere. It should have been 2, not 12, or something like that. Then just take it out. Consider the effects of any outliers that are not known errors. If we have outliers and they're not errors, why did that happen? We want to consider something is happening and it's changing the way my line is going. It's either becoming a better estimate of my y value or it's becoming a worse estimate of my y value, depending on what those outliers mean. Let's look at the note. Requirements 2 and 3 are simplified attempts at checking these formal requirements for regression analysis. There's a more difficult way. For each fixed value of x, the corresponding value of y have a normal distribution. For the different fixed values of x, the distributions of the corresponding y values all have the same standard deviation. That's important. For different fixed values of x, the distribution of the y values have the same standard deviation. This is violated if part of the scatter plot shows points very close to the regression line, while another portion of the scatter plot shows points that are much further away from the regression line. For the different fixed values of x, the distributions of the corresponding y values have means that lie along the same straight line. These are samples, and we want to make sure that the samples are mimicking the population. Finding the equation of the regression line. Round B1 and B sub 0 to 3 significant digits. It's difficult to provide a simple universal rule for rounding values of B sub 1 and B sub 0, but this rule will work for most situations. Please make sure you follow the directions in MATLAB. In my equation, this value would also be known as the constant. Use StatCrunch to find the equation of the regression line in which the explanatory variable, which is the x variable, is chocolate consumption, and the response variable, which is the y variable, is the corresponding Nobel laureate rate. I've preloaded these values. We have stat, regression, simple linear, X is chocolate, Y is Nobel, compute. This is the regression equation, the slope, which goes along with the slope next to chocolate. Chocolate would be the X. If I were to write this differently, I could write this as y equals negative 3.367 plus 2.493x. That's your regression equation. And your slope and intercept are here. Requirements. The data are assumed to be a simple random sample. The figure is a scatter plot showing a pattern points. This pattern is very roughly a straight line, and there are no outliers. The requirements are satisfied. I know it looks like these 2 points are outliers. They're not really outliers. They're not far enough outside of the normal realm of the graph to be called outliers. If I press that button, I have the equation of this line. Solution. We should know that the regression equation is an estimate of the true regression equation for the population of paired data. That's why we call it y hat. The y hat means it's an estimate. If it said y equals beta sub 0 plus beta 1x, that is no longer an estimate. That is the true regression equation for the population. One particular set of sample data, but another sample drawn from the same population would probably lead to a slightly different equation. The equations are really based on what points were given for that particular sample. You can see that the regression line fits the points well, but the points are not very close to the line. It does fit the points. You can see that this is somehow going through the middle of these points. Even this point and this point are almost the same distance from this line. Making predictions. Regression equations are often useful for predicting the value of one variable given some specific value of the other variable. When making predictions, we should consider the following. Number one, if it's a bad model. If the regression equation does not appear to be useful for making predictions, then don't use the regression equation for making predictions. For bad models, the best predicted value of a variable is simply a sample mean. If we have a good model, we use the regression equation for predictions only if the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well. Even though we don't really know how chocolate and Nobel laureates are related, we do see that the regression equation fits the points reasonably well, so we'll consider it a good model. Correlation. Use the regression equation for predictions only if the linear correlation coefficient R indicates that there is a linear correlation between the two variables, and we talked about that in 10.1. Scope. Use the regression line for predictions only if the data do not go much beyond the scope of the available sample data. I'm going to highlight this. If I know on my graph that I have these points and they go from 1 to 10, and I have these points and they go from 1 to 50. If I pick for X a value of 100, that's considerably far outside the scope of my regression line. I don't have any data for X equals 100. Something else could be happening as X gets bigger. We have to be very careful using this line to make predictions very far from where the data is. The strategy for prediction values of Y. Is the regression equation a good model? The regression line graph in the scatter plot shows that the line fits the points well. R indicates there is a linear correlation, and the prediction is not much beyond the scope of the available sample data. If that's true, We go here and we can substitute some value of X and get a value for Y. If that's not true, it's not a good model, then we do not use the regression equation. Predicted value of Y is the value of Y bar, which is the mean of the Y values. If we have a good model and everything seems to work out well, we can use our regression equation. If we do not, then find the mean of the Y values, and that will give you the best prediction. Use the chocolate Nobel data to predict the Nobel rate for a country with chocolate consumption of 10 kilograms per capita. Go to StatCrunch, and we have all our data. Go back to Options Edit, and go down to Prediction of Y. I'm going to put 10 kilograms. I hit Compute. We have our same equation. That's not going to change. But now we have predicted values. When X is 10, Y hat is equal to negative 3.37 plus 2.49 times 10. We can just plug it in and we get our predicted value of Y, which is 21.6. They round it and we're using the full values, so that's making a little difference. Predict the IQ score of an adult who is exactly 175 centimeters tall. Do you think that IQ has anything to do with the height of a person? Hopefully you said no. For B, this is a bad model. We're going to use Y for predictions. Knowing that there is no correlation between height and IQ scores, we know that a regression equation is not a good model. The best predicted value of the IQ score is the mean of everyone's IQ, 100. That's the population mean. Making predictions, interpretation. In part A, the paired data results in a good regression model. The predicted Nobel rate is found by substituting the value of X into the regression equation. In B, there's no correlation, so we use the predicted IQ score, the mean of Y bar equals 100. Key points. Use the regression equation for predictions only if it is a good model. If the regression equation is not a good model, use the predicted value of Y.